Okay, well, we're going to talk about section 2 now. This is going to be more the machine learning and material science stuff that you're expecting. Now, if you've skipped section 0 and 1, that's great. I assume that means you have Python already installed and are familiar with using it, which I've kind of assumed a little bit. That said, make sure that you do have Python 3 and the necessary packages listed above. So these are just packages we're actually going to be using in the code. If you run this, it should tell you whether or not you have what you need as an output. If you don't have them, feel free to just install them as you go as they come up. It's not a huge deal. But yeah, I just want to make sure that we've covered that if you need the help there. So let's talk about what our overall goal here in section 2 is. So we want to grab material data, and we want to get that data and format it in a way that we can use it for machine learning, and we want to visualize it and just make sure that everything looks okay before we actually throw some machine learning algorithms at it. So the first thing we're going to do in order to grab this data is we're going to import pandas, and then we're going to display what the data looks like. And before we do all of that, let's talk about the data that we're grabbing. So this is going to be inorganic heat capacity data from the NIST JANF tables. So I have that open right here. Here's an example of hydrogen. So hydrogen is not a great example, but we can look at something that forms crystal, that CR. And this is data with this tag right here. All of this data had that crystal tag on it. So lithium hydroxide, that could be one. I'm not sure exactly what that is, but we can look at it. Okay, so yeah, you can see that the liquid transition happens at 477. So here at room temperature, we are in fact crystalline with a heat capacity of 49 joules per mole Kelvin. Awesome. So this would be one example of an instance we expect to show up in this data. So I've gone ahead and gone through a bunch of the data on the JANF tables and compiled a list of formula and heat capacity. So just the two things, just formula and heat capacity. But I've compiled a big list of those, and I have close to 300 compounds that we're going to try and do some machine learning with. So I've saved that as a CSV, which can be downloaded from Google Drive. Just follow that link right here. So this folder right here, this heat capacity.csv, we can go through and quickly look. It's got formulas and heat capacities. And there are 277. So for now, you're going to want to download that. You're going to want to download everything on that Google Drive folder if you're going to follow along with this tutorial. The Python notebook that I'm using is right here. So this notebook that we're looking at. And if you don't want to code this all up yourself, you can just open up the notebook and run through each line of code. So now that we have an idea what the data looks like, we're going to use the pandas package. Again, pandas, I imagine it does everything Excel does to some extent. So we're going to import the pandas package. And then we're going to use the read CSV function in the pandas package. So I import it as PD, meaning I don't want to type out pandas every time I want to use stuff from the pandas package. So PD is effectively the equivalent of the pandas package. So pd.readcsv, and then put in the file name as a string. So these guys represent these quotation marks. That's how you denote strings. And then to visualize the data, I use .head, and it just gives us a brief overview of the first 5. Head has a default value of 5. First 5 rows in our data. So you see there's only 2 rows. So we have the chemical formula and then the heat capacity. But we're going to create more data than just that in a second. So once we've created a data frame, so this is our heat capacity data frame. Read CSV creates a pandas data frame when you use it. We want to be able to access both the formula and the heat capacity individually. So the way to do that, the way to access a single column is to use these square brackets and then the name of the column. So here, property heat capacity, I just copy pasted that here. And then again, I made sure to denote it was a string using these quotation marks. And then I'm going to do list splicing because I don't want to see every instance in this column. There's 277 of them. I just want to see the first 5. So I will use this right here to look at the index value 0 to 5 on this column here. So then we look, and in fact these values do match up, so that's great. We've accessed, so this sliced list I called it, we've accessed the first 5 instances of the heat capacity column. Okay, so that's just, you can do the same thing with the formula, and we'll do that in a little while. That's just a brief introduction on kind of a reason you'd want to use pandas. It's easy to look at your data and play with it. Now, speaking of looking at our data, let's go ahead and do that. Let's try to see the distribution of the heat capacities for the data we've pulled. We use the Seaborn package for this. I'm sure there's other good packages that can do the same thing. This is the one I've seen before and familiar with. The first thing we're going to do is allow for plotting. Now in Python, you can do pretty plotting similar to like what you'd see in, what's that? MATLAB. So it's similar to MATLAB style plot. That's why it's called matplotlib. And then for Jupyter, you have to do this little %matplotlib inline, this little line of code here. And that'll let it actually display on your notebook. If you don't have this line, even though you can use the plot functions, it won't display inside of your notebook, which can be a little annoying. So just put both of these guys here, and that'll allow us to do plots. So then we'll import Seaborn as SNS, again, because I don't want to type out Seaborn every time. And then we use SciPy, which is scientific Python. From SciPy, we get norm, which gives us this beautiful normal distribution here. And then we get stats, which allows us to access a variety of stat functions. So this is just importing some stuff. And then finally, we want to look at heat capacity. So we'll look at distribution plot of heat capacity, and then we'll look at the column, we'll do the distribution plot of the data frame, heat capacity data frame. We'll look at the column for the actual heat capacity value, and we'll fit that to a norm. And so we can see this distribution. It doesn't fit the normal perfect, but it's not bad. It's pretty close. It's a little skewed and stuff, but that's fine. So if we look at the probability plot, ideally for this to be a perfectly normal data set, it would lie right along this red line. You can see that it doesn't. There's a little bit over and underrepresentation in some values, but it's fine. We can probably use this data. It doesn't look awful, or we could attempt to normalize the data. So the reason we're looking at all of this is most machine learning algorithms, they require normalized inputs, but they also do better if they're trying to predict unnormalized data as well. So an example is if I have 1 million examples of values of like 1,000, and then one example of a value of 10, it's really weighted towards the values of 1,000. And you can kind of understand that if you're making predictions, it's really easy to just always default to 1,000, even if 10 is like really, really big giveaway. Yeah, that's probably not the best example. Just if you're curious, you can look it up. There's a lot of reasons to normalize your data. For now, we're probably not going to normalize it, but we're going to look at some methods we could use to try to normalize it if we were really worried about it. So what we're going to do is consider some transformations. Here I've talked about considering a log transformation, so we can look at what that looks like. So if we import NumPy has a lot of math functions, matrices, arrays. It's a wonderful computing tool for science. If we import NumPy, we can do numpy.log, which grabs us a log function. And then we can transform each value. So this is a little tricky. It's going to do the log function for each value inside of this array or this column. So it'll do the log of 24, and then the log of 100, and then the log of 56, etc., etc., etc. So the shape and size and all of that for this column doesn't change. It's just the values are scaled by a log. So if we look at that, we'll do the same plotting. This is now the data with the log transformation. It seems like it may have improved, but it also seems like it's not perfect. Especially looking up here, you can see it almost matches. It's almost as off as the other guy. So we can try another one just really fast. So let's do a square root. And you can see this one looks much better up here, and it's just a little bit off on these edges again. Now for now we won't use any of them, but that's kind of an idea on what you would look for if you are worried about normalizing, which for some other data that might be a lot more important. But for now this is just kind of a proof of concept data set, so we're going to go ahead and move on and not worry about all the extra steps involved with handling that process. So now we're going to move on to how to make this data appropriate for machine learning. So currently we only have the formula and the heat capacity. So with machine learning, what you want to do is you want to have a lot of features, or at least you want to have important features that you can correlate to the property or the target. So in this case, we're going to call heat capacity our target, and we're going to turn the formula into many, many features based off of the composition of that formula. So AL1, BR3, each of these elements, they're each unique, and they each have different physical properties, and we'll use those physical properties to make a feature vector which can be used in our machine learning. So let's look at briefly how we do that. So make feature vector from formula. I've written this function here called getFeatures. It's not too nasty, but it's probably not worth going over exactly how it works here. A couple things. It does use the PyMatGen package, and we are going to have to import some elemental properties. So if we look at simpleelementalproperties.csv, for each of the elements, we have certain values. So we have atomic number, period group, quantum number, covalent radius, crystal radius, etc., etc., etc. Now, for some things, there will be missing values, and that's fine. If we look let's see, yeah, like out here, work function or bulk modulus doesn't make much sense or sometimes we just didn't have the data to give values to those things. So sometimes we'll have missing values, and I'll talk about how we handle that in a second. But what we're going to do is we're going to read in our formula. So I have an example down here. We're going to do the example on NaCl. We're going to read in our formula, and then we're going to get the composition of that formula, so the percent sodium, the percent chlorine, and the total amount of sodium and the total amount of chlorine. And we'll get those from the PyMatGen package, so mg.composition. I imported PyMatGen as mg. So mg.composition formula, and I give it fractional composition and elemental composition. And then from there, that would give us for each element we would get that value. So from there, I either average those values or I take the sum of those values. And then I can also take the variance of those values and the range of those values. I can make another video about this because I think this is a key concept. But for now, we'll move on saying I took all of the elemental properties for the formula, and then I averaged them, I added them, I took the variance of them, and I took the range of them. So to demonstrate that, we use NaCl, and to show how the function works, which is all you really need to do at this point since the function is mostly complete. There may be updates in the future, who knows. But you simply, as a string, put in the composition, or the formula. So in this case, I put in the formula NaCl, and I save the output of that to the variable example vector. And then here I'm going to print off just a little statement. So it looks at the length of that vector to see how many features there actually are. It says a vector with 228 formula-based features has been created. Now, if we really want, we can also print off the vector itself. So I can go in here and do print then example vector. And so this is what the vector itself looks like. So you can see there are some not a number of values. And there are just a bunch of it feels meaningless because they don't have labels with them, but a bunch of data that describes the interaction of or the differences or the sum of the properties of sodium and chlorine. Let me go ahead and delete that. Okay, so now that I've created that vector, I just want to make sure that that vector gets saved. So the vector for sodium chloride, I want to make sure it gets saved to the property, the heat capacity, or the target, the heat capacity of sodium chloride. So here I'm going to make two empty lists, one for the features, which is this example, it's going to be similar to this example vector, and one for the targets, those are going to be the heat capacities. And then here I'm doing the for loop for formula, comma target in zip, heat capacity data formula, and heat capacity data, heat capacity. So it's going to, with this zip function, it's going to say, for the first instance in here, assign it to formula, and for the first instance in here, assign it to target, and then run through the loop. And then go back to the top of the loop, and for the second instance in formula, assign it to formula, and for the second instance in heat capacity, assign it to target. So what we do there is we make sure that the formula and the target are always paired together, so they never get pulled apart and then put back together. That way we're making sure that the formula vector matches the property, or yeah, the feature vector matches the property it was associated with. So in this loop, what we're going to do is we're going to append to this features list the output of get features. So if you remember, the output of get features is this vector with 228 features in it. And then to targets, we're going to output the target, so the property associated with that formula. In this case, the heat capacity of the formula. So if we were to put NaCl through here, we'd have NaCl as the formula, and then the heat capacity as NaCl as the target. So then the output would be a feature vector for NaCl showing the variance, the average, the sum, and the range of the values of the individual elemental properties for NaCl. And then in here, we would just put the heat capacity of NaCl. So once we've done that, I'm going to turn this, or I'm going to make a data frame of the features. I'm going to make a data frame, or I guess a series, which is important that it's not a data frame, a series of the targets. So the reason we're doing this, and let me make an awful illustration in Paint, is in the scikit-learn package, your functions need, let's go here. Usually the function looks like this. Like it'd be like random forest regression. And then it would have an input of your features, so usually they call that X train, and your targets, so Y train. So X train, we can call this features, we can call this targets. Oops. And so what it expects is it expects features to be a fatty matrix, essentially, and it expects targets to be a single column of data. So this would be targets. Ooh, that doesn't work how I expected. So this right here can be targets, and this right here would be your features. Now they'd have the same number of rows, so this would be a value of n, And here this row would correspond to this row. And you might have, and here we'd have our 228 features, so 228 columns. And here we would have one column, which is our property, or heat capacity, CP. Okay, so that's kind of the end format we want to get at. So here we're going to make a data frame, which is, like an Excel sheet, and then here we're going to make a series, which just represents a single column. So for our features, we're putting them into our data frames, this fatty block, and then for our targets, we're putting them into a series, or just this single column, which will be fed into our machine learning algorithms in a little while. So now that we've turned our formula into features, and put those features into a data frame, and put our target into a series, we are going to do the final step, which is going to be dropping the values that we don't want to have. So an example is, if there was a chemical formula with an element that I don't have in my database, which I have a few that are just missing, every single value in your formula feature vector is going to be not a number. There was going to be a math error, and it pooped out because there was an empty value, as we saw earlier. There was an empty value here, and it doesn't make sense to add an empty value. You can add a 0, which is fine, but to add an empty value, it's just not a number. So we have a few of those. So anytime an element in the formula isn't in our database at all, there will be an error that prints out for you, and then it will have an entire column of empty values. So we're just going to go ahead and drop. So we're going to do drop NA, and then how equals all. So we're going to drop the not a number values, and then we're going to drop it only if every single column in that row is not a number. We're going to drop the entire row. And then over here, then we're going to reset the index, which is just a little bit like, I'm not sure if it's necessary, but I like to make it look pretty. Now the index, really quickly, are these values here, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. If I were to drop this value, it would not appear on this list anymore, but my index would go, it would go 0, 1, 3, 4, and this 2 would be missing because I dropped 2. So after I drop everything, I'm going to make sure I drop it for the features, and then I'm going to drop it for the target as well. So what I'm doing here is, after I drop that value, the index value is missing, so then I set my targets to only have the same index values as my features. And then I reset both of them. So now if 2 was missing, that entire column's gone, and then it starts counting 0, 1. Then when I reset the index, it starts counting from 0, 1, 2, 3, 4, 5, 6 again. But that row that I dropped is now just not included in the data set. Then after I drop those values, for the ones that I keep that have not a number values, I'm going to fill them with the average or the mean value of that column for the entire data set. So if we were to look up here, oh, actually, this won't really work, but let's say 100 was missing here. So I don't know what the heat capacity of this is. A method to fill that value would be, well, what's the average of everyone else? And to put that in there and see what happens. Now you can play around with different methods of filling. This one seems to work for now, but it's definitely a place that we could look at improving if we were to try and build up on this example. Okay, well, thank you. I think that's it for section 2.